So I want to welcome you all to today's SLAM seminar. It's the fifth in the series this fall. For those of you who are new to the audience, the purpose of this SLAM seminar is to bring together people from on campus and off who are interested in using data to understand our academic mission. So we're really happy today to welcome David Pritchard. Professor Pritchard received his bachelor's degree from Caltech and his PhD from Harvard, where he worked with Professor Dan Kleppner, who then brought Dave with him to MIT as a postdoctoral fellow. Pritchard joined the faculty at the Department of Physics in 1970, and he's currently the Cecil and Ida Green Professor of Physics there. Professor Pritchard's research laid the groundwork for the field of atom optics, a field which has exploded in importance in the last few decades. His lab has been a hotbed of innovation for more than 40 years, and among other things, it's been the training ground for several Nobel laureates. His work has been recognized with many honors. He's a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences. During the 1990s, Dave turned some of his attention to teaching reform and led the creation of something called My Cyber Tutor, a sophisticated online homework system that can tutor students through physics problems and allow them to continue working on them until everyone gets them right. This system has since been commercialized by Pearson as Mastering Physics, and the engine of it has turned into mastering everything else, mastering astronomy and biology and geology, and it now serves about 4 million students, I think. Quite an enormous exercise. Over the years, he has focused a physicist's eye on all of this, recognizing from the start the power of the data that computerized interactions with students produce, and working to understand what it tells us about student success, thinking about how best to use this kind of information. His talk today will be on the topic, what are students learning from what activity, and is that okay? And on a personal note, I just want to say that the quality and the excitement of the work that Dave's group at MIT has done on this topic really played a central role in my own first forays into this kind of work, and so in a sense helped to provide the motivation for this whole seminar series. Dave.
Oh man. Well, thanks for that introduction. That's the kind of thing that people say when you get old. Okay, so I'd like to talk to you today, about the things involved in this title. And so we might as well get going. Some of you may know Andy Paul. He was a U of M student. So I think that the biggest switch going on now in education is the change in emphasis from teaching to learning. And of course, to do that, we have to assess learning. And well, how do you do that? Usually you compare two assessments, an earlier one and a later one. The first work that I'm going to talk about is actually comparing two groups of students who are 2 sigma apart in their standing on the exam, and later that will be justified by the fact that some of our interventions are producing a 2 sigma effect. So that's why we picked the 2 sigma. Okay, so fine. So that's just an overall assessment. Now, what are they doing that causes them to learn? I mean, if they're learning 3 times as much doing homework as they are in class, why do we insist they come to class? I mean, maybe the fact that they don't come to class shows a better appreciation for how they really learn than we do. But it's harder to determine. And then I think what's much more important, which is significantly more important than which topics did they learn, is what habits did they learn? Because they're going to forget the topics. And I'll present evidence to that effect. And then the question is simply, are we teaching the right stuff? And according to whom? Them? Us? You know, the universe? Somebody? Anyway. So when I say problem solving, that's a very undefined term in the literature. And what I mean is a problem that involves 2 concepts or multiple concepts in a way that the unknowns are not in a single formula. So you have to use energy conservation to figure out how fast this ball is going to be going when it comes to over the edge here, and then kinematics to find out where it lands. But the question says, if you release it from here, where does it land? It doesn't tell you there are 2 parts. It's not a part A, find how fast it's going at the edge, and part B, find where it lands. So the students have to understand the pieces and how they fit together. And we even try to teach them to do that, which most courses and most textbooks do not. And then I'm I come from physics where data is well known to trump opinion by a lot. And in education, this will in the future allow scientific improvement of education, and it's already doing that to some extent. So, okay, so let's look at our 2 sigma stuff here. So what we did very simply was we took, 400 something student, 500 student class. We took 2 groups, one that was 1 standard deviation above the average and one standard deviation below the average. And we just looked in detail at these 2 groups. And in my mind, the A group here is a reasonable expectation of what we might expect students to know at the end. And the C group is we actually pass those students without reservation. Okay, usually the passing is 1.2, 1.3 standard deviations below average, although we set it by an absolute scale. So what we're investigating is what the A group learned that the C group didn't. And so the first thing that we did was we analyzed the analytic or symbolic answers that the students in our institution never do numerical problems. Everything is symbolic, which is not the way to teach, but I probably won't come back to that point. And so we analyzed just the following question, so there were 2 principles. Did they understand identify the 2 principles, and did they know whether they applied A first or B first or both simultaneously? That's what we mean by doing well. That's essentially the quality factor. Is to what extent was their thinking okay about the principles and how to combine them. And and 5 here means they basically got the answer perfect. 4, well, maybe they didn't understand quite the constraint due to the pulleys, but they did understand the physical principles. And 1 is basically, as some of my less tolerant colleagues say, clueless. And 2 is just maybe they had 1 clue, but not 2. Okay, so what this shows is pretty obvious that, yeah, the C students were, 20% lower than the average, and the other guys were 20% higher than the average in terms of the score they got with our partial credit grading. But when you look at these extremes here, you see 5-to-1, 4-to-1 ratios. So then a lot of these problems, we asked the students for a written plan of attack. And what we found there was we hadn't taught them to do written plans of attack, and what we really meant by a good plan of attack. And so half of the plans of attack did not contain the information that I just mentioned. What 2 concepts do you use? Which order? And basically that would be enough to write a fully accessible plan, and half of them were incomplete, independent of the quality of the students. But of the ones that were complete, then again we saw this ratio of 4, 5-to-1 in terms of the good students and the C students and the A students. We also have considerable evidence that this is in fact what is learned, because the students who repeat the course learn about 2 sigma in the repetition of the course. So the students a little bit worse than our low group here would fail the student course, have to take it again, and then they would come out somewhat above average. Okay, so let me just summarize it. The C score is 79% of the average. There's 20% of the stuff they didn't know. That's the partial credit way of thinking about it. And the A's, and they had 62% of the credit that the A's do. But the A's were very good or excellent on both analytic and verbal 4 times as often as the C's, and the C's were wrong, invented principles that didn't exist, didn't realize that energy was conserved 4 times as often. So that's a pretty big difference. I don't think, so let me just say the conclusion. And this is the title of the paper that we've just submitted. Partial credit grading rewards partial understanding. I'm not saying if that's good or bad, I'm just saying that's the way it is. And if you think about how you get a 5-to-1 ratio, it means that the Sigma Plus students are getting essentially the problem right 65 or 70% of the time, and the C students are getting the problems conceptually all together less than 20% of the time. And the students who are at the passing edge are probably doing it less than 10% of the time. Okay, so do you like that? Anyway, that's the way it is. Okay, so now let's try to figure out in a course what activities students are learning from. And really, we can use pre and post testing, and then we get some sort of gain, some sort of improvement. Whether the tests are identical, turns out that doesn't matter very much, or whether they're calibrated together by some item response theory or whatever. And then we look at what the students who had a lot of improvement did. We just look at what activities they did. So this is just it's a correlation study. And the course activities were recitations, written homework, online homework, group problems, and then, as I said, we correlated everything together. And remember, this is just a correlation. Any causation is by inference. Okay. So, here are the results. This course is the spring semester introductory mechanics course, and it is largely for students who failed to get a C or better in the fall course. And so, in fact, for 70-something% of our students, we had a final grade in December, and we had a final grade in May. And we looked at the improvement and what it correlated with. And we've used a variable extrapolated gain here, which is a mouthful, and what it essentially means is this is our best judgment as to how much of what you didn't know in December you did know in May, given that you did all this activity versus none of it. Okay, so this is regression stuff. So the winner here is mastering physics, and the written homework, there's no correlation, and the class participation is not significant. In fact, we've measured this for the FCI and a bunch of other things several times, and it's come out negative as often as it's come out positive. I mean, measured the learning and correlate with how much the students go to class. So we don't know. Maybe the students who don't go to class do something more effective, or at least equally effective. We don't know that. And the group problems looked positively correlated. So that at least one year it was quite significant by the usual 0.05, and the other year it wasn't. And obviously this is statistically significant. Whether it's systematically significant, I don't want to say.
So Dave, can you talk about what you correlated with, their performance on mastering?
Okay, we looked at the gain. The gain is what grade did they get in May minus what grade did they get in December. Okay, and then we correlated that with how much of each activity they did.
So just how much they completed the mastering physics?
That's right. It's completed, yes. And I mean, technically in the group problems we use the grades, but the grades are usually, I mean, there's not that much difference between a 6 or a 7 and a 10 compared to an 8 and a 0.
Yeah.
And
so
it's mostly attendance. Right. And so basically, when you figure out the mastering, you get 2 standard deviation of improvement. And so that's one of our motivations for the 2 standard deviations. Okay, so that's I think really right now about the best we can do. Maybe you guys can do better at figuring out what particular activities are actually helping the students to learn, or at least correlated with that. Okay. Now, so I'm going to tell you the plan of this talk, but I've already given two topics of it. The A versus the C students, and the correlation study of what people learn from. So now I'm going to talk about mastering physics, which really is an online Socratic tutor. And in fact, when I did this the way we all traditionally do education in physics. Well, I saw the problem. I said, okay, so kids doing homework, I mean, they get stuck in the middle of the night. What happens then? So I want to, I have a little Mephistopheles, and I'd say, well, Bill, you're not getting anywhere and you still have to do your chemistry problem. Would you settle if I broke this into 4 parts, but they were only worth 2 points apiece instead of the 10 points you got now? Would you take the deal? And well, when you try something like that, the students say, what kind of a tutor is this? It's the most unfriendly thing in the world. It takes away points. And when I don't know stuff. But anyway, okay, so that's the next thing, and then talk about the data mining that goes with it, and then I'll talk about the habits later. So this is mastering physics, and actually it comes up without this hint panel. But But the criteria that we used, and I'm talking about our younger son and I, we said we're going to have to demand the appropriate response. In other words, if it's a vector diagram, we have to figure out how to draw vector diagrams. If it's symbolic, we have to figure out how to grade symbolic. Of course, we can grade multiple choice, we can grade single words, but that's actually tough because people can misspell them, they can add an S on the end. Is it gravity? Is it gravitational? Is it due to gravity? Anyway. And the other thing was it had to be for the grade, because people just toss it off if it's not for the grade, and if it's for the grade, they'll bitch every time they don't like it. But that's how we're going to learn to make it better. And so there is a requestable list of hints. So this is the format. And the first thing is they submit something and there is feedback. But over half the answers get spontaneous feedback, even to analytic problems. We can't do that for numerical problems where you randomize the variables. There's just too many. We can't sort that out. But for symbolic things, you can look at them and you can see what the student is thinking about. Or you can challenge them. So this one is an automatic. Check over your trig. We have a little thing that substitutes all different trig functions, that if it then gets the right answer, it says check over your trig. And what happens is the students use that as a crutch. They'll come and they'll say, oh, I can't figure out what's wrong with this question, but I know it's not the trig because I didn't get the message to check over your trig. When in fact our algorithm isn't that sophisticated, and it really was that it didn't know some cotangent identity. Okay. And then we have specific responses where we see that a lot of students have given this answer, and then we try to create cognitive dissonance. We say, so you just calculated the acceleration of the block on the plane. That's the problem. And then you say, so do you think that the block accelerates with the acceleration of gravity when the plane is level? And it will that will be the hint. Well, obviously not. But plug theta equals 0 in my answer, and gee, it does. Okay, so that sends them back to try to figure out what's going on, which is what you want to do, I think. Okay, and then we have declarative hints who just say, well, how to approach this problem. And then we have Socratic hints or procedural hints where there's some subtask. You know, maybe to do the first part of the problem or the second part of the problem, or to calculate the x components of forces along the plane or something like that. So that's how it works. Okay, now as Tim was alluding to, so I'm preaching to the choir here. The point is that at the end of the term, on these problems, typically the problems require a couple of different answers or responses, 2 or 3. And altogether there's a log of the 10 back and forth transactions between the student. They submitted a wrong answer, they got some feedback, they submitted the right answer, they were told it was okay, they got really stuck on the next part, put in a wrong answer, asked for a hint, blah, blah, blah. So we have 10 times 120 or however many problems we assign times 450 students. But for each student, we have 10 to the 5th bytes. Now compare that with a grade book. The grade book, you know, homework 1, 2, 3, 4, 5, you know, test 1, test 2, test 3, the 3 quizzes and a final. And how many times have you heard him, well, look at those grades. It seems like he's going up on the test, so maybe we ought to fudge the grade up. Come on, if you know the size of testing error, you know that you're talking malarkey. Statistically speaking. Okay, so what are we going to try to do with all these data? And so fine-grained assessment, I claim, is the holy grail. Being able to assess the detailed mental state of the student, which is a guide for the teacher, but it's, you know, for the class, but it's also ultimately will guide individualized tutoring for each student. Okay, so that's the goal, that's the holy grail, I call it. Now, also, it turns out, I think, very important are habits of mind and behavior. And so I'm going to talk about habits that either help or that hurt. So I'm just going to start talking about the first question. This is actually a question for you. When do students do their homework? Okay, so this is a quantitative question. This is not a rhetorical question. The assignment is due Tuesday night at 10 o'clock. And now the students have all requested later, so we do it later. But then it was due at 10 o'clock. And the question is, what fraction of the homework is done at midnight on Sunday, which is long before the students go to bed on Sunday night? Okay? So how many people, and let's just restrict ourselves to the half of the class that's actually taking it seriously, okay? And I'll explain what that phrase means in a moment. Okay, so how many think that the kids who are the half of the class, the majority of the class, who take the course reasonably seriously, have done over 10% by Sunday at midnight when it's not due until Tuesday night? Over 10%? How about over 20%? Okay, well, we've wiped it out. Okay, I'll show you the data. These data are arranged by what fraction of students of the submitted problems are copied. And I'll get to that in a minute. And half the class is in this top bin here, copy rate less than 0.1%. And here, Sunday night, they've done half of the problems. Did you believe that? I mean, do you believe the data, or do you believe your prejudice? The prejudice of everyone, the judgment, the good judgment of every teacher in this room. Okay, well, the data, that's what it says. I mean, we know why it happens. You go to dinner and you beat your chest. Oh, I haven't started my physics homework and I have a chem test tomorrow. I'm going to have to pull an all-nighter. Oh, I'm a big gorilla here. You know, if Tim's sitting next here, he's actually done it all. Is he going to pipe up and say, Dave, you're really an irresponsible student. You know, you're just screwing yourself. You should really do all this homework in advance the way I have. Chris, I mean, sorry, but you know what we'd do to Tim if he said that? What the other students would do. So I think that's why we have such a bad approach. So what do you study? Well, we studied time. We said that's the variable that's really important in people's lives. It's really important in a lot of psychology about learning curves and stuff like that, experimental psychology. And we never had any data on that before, except how many points the kids could get in a 3-hour test or a 1-hour midterm. So we started looking at the curve for how how long it took the students to submit the answer from when they opened the problem, or to ask for the answer. And so this is a log of the time scale. So here, you know, at 7 minutes, this is a 7-minute problem, and that's pretty nice because there are a few kids here who get it real quick, get it perfectly without any wrong answers. The blue curve is students who made at least one wrong answer, and the purple curve is the students who asked for a hint. So that all makes sense, right? These 3 curves coming in one after the other makes a big curve. In fact, it's published in the Journal of Analysis of Behavior because we have the best data on the shape of that curve, which turns out to be log normal, whereas people before had always assumed it was normal. And we showed some nonsense. There's a paper with pretty good data on 6 nonsense syllable remembering, and it was Gaussian too. I mean, we just had so much data compared to previous experiments because we had a curve like this for 150 different problems. And we had 450, like in this, people on it. And then obviously these kids were doing it the next day. And then these kids are the geniuses that we had at MIT because they get it right in 50 seconds. If you believe that, you're not one of those geniuses. Because that means they copied it from someplace. And that's our definition of copying, and that's how I was able to tell you what fraction of the problems were copied on the previous problem. In fact, if you look at it, they respond in less than a minute, and that's insufficient time to read the problem and enter in the answer, okay? And they're all correct on the first try over 90% of the time, which no one else is. Okay, so that's what we mean by copying. Now, here are how the test scores correlate with the amount of copying. For the pre-test, the concept test, well, it's a mechanics baseline test, so a little more than concepts. The first midterm, second midterm, third midterm, and the final. This is a z-score, so this 0.40 is 1 standard deviation. Well, as you can see, they're essentially equal. The standard deviation means essentially equal when they walk in that class the first day. And by the final, there is a substantial difference. And if you extrapolate to using no homework copying versus all homework copying, you get something a little bit over 2 standard deviations. 2 standard deviations, if you look at Bloom's taxonomy, that's from a dedicated personal tutor who uses mastery tutoring to tutor you for the whole course. This is due to one element in the whole course. This is a whopping strong signal. And in fact, we can look at it differently. We can just look at the final exam score versus the fraction of homework that they copy. And you see this incredible curve here. But this is actually 2.4 standard deviation because we haven't looked at the whole final exam. We've only looked at the part that is analytic problems or symbolic problems. That's the only problems for which we see this three-hump distribution. On multiple choice, there's some literature from ETS people about how there are all kinds of intermediate guessing heuristic methods, and so it's just a big blur. But on the analytic symbolic problems, there's this three-peak distribution every time after time after time. But it correlates great with the analytic final exam. But what about the mechanics baseline? Well, here's the mechanics baseline. There it is before the course, there it is after the course. And so you can see that basically copying your mastering physics does not change the slope of this curve. So I can, in fact, just go over that. This is the killer here. Students, we probably don't copy the homework on those, on the kind of concept questions because you can answer them really quickly, and they do go in on Sunday night and work a couple of easy problems. And then the students did copy the tutoring on the analytic. So what we see here is that we're confounding the experts. And what I mean by that is the following. The mechanics baseline test has conceptual reasoning questions, and it has numerical questions, some of them being two-concept numerical questions. So, according to my expert view, in order to solve an analytic problem, you start off with conceptual thinking, right? And then you figure out, oh, well, okay, so momentum's conserved because there's no external force. Okay, so I have the momentum equation and blah, blah, blah. So then I get the analytic answer. Now, if it's a numerical problem, then I say, oh, yeah, I plug the numbers in my symbolic expression to get the answer. Well, how do you explain this if the students work that way? How can their performance on the analytic problems not depend on their performance on the concept questions? How can their performance on the numerical questions not depend on their performance on the analytic questions? Answer, my answer, they don't learn physics. They learn to do the kinds of problems that we have on the assessment. And the way that they do them is not the way we explain them in class, and it is not the way an expert does it. They do it by formula hunting, by making an analogy with a problem that also had a pulley or a plane in it. And you'll hear the students talk about pulley problems. Not energy problems or momentum, they'll talk about pulley problems or collision problems. Okay, so there's a big gap here. Okay, so this is a huge correlation with a single activity. Among other things, it shows that the kids who are copying the analytic problems can learn physics. At least they can learn the other stuff because they learn 1.3 standard deviations of that. And so I think it strongly suggests that causally, if they did the mastering physics, then they could learn to do the analytic problems too. However, on the other side, it also implies that mastering, in spite of giving you the hints that go through the problem the way an expert does and forcing you to work through the problem that way, does absolutely nothing to help you learn conceptual reasoning, as given on these multiple. So I don't know what to make of this, but fundamentally it's what I said. They don't think like experts. Okay, now do I have time for this? 25 minutes, 23, yes. Okay, so I don't want to leave you with the idea that everything is bad. What about a good habit? So, okay, so remember what mastering is there's multiple paths that you can go through. You can answer it and get it right, you can answer it and get it wrong. So here we see that 29% of all the students fail their first attempt. And then they have various ways of getting through to the second attempt. And so they might get no feedback, or they might get useful feedback only, or they might get some hints and subtasks and so on. And then they make a second attempt. And now there's 11% of the students down here who look at the problem and said, I'm so confused or so uncertain that I'm going to pay the penalty, which is small, to open up the hints before I even try to answer this, because there's a 4% penalty for a wrong answer and only 2% penalty per hint, but they would typically have to use several hints. Okay, so now we developed a way of using item response theory to measure the shift in their skill from what you expect to how they actually performed. And the group that just got no feedback were, on the second attempt, they were almost a standard deviation low. And all that is saying is this is sample bias. These kids were picked out to have the answer wrong, and in fact further picked out that the computer didn't recognize what was wrong with the answer. And they're pretty confused, and the next attempt they're still confused. The kids who got the useful feedback or who got the feedback and hints, used the hints as well, they had a positive. The second time they did better than you would have expected had they not seen the problem ever. It was the first time that if it were the first time they did the problem. That's slightly statistically significant difference, but not all that much. The big surprise is those kids who were so confused at the beginning that they started off and said, okay, I'll pay the hint penalty, did 1.5 standard deviations better than you would have expected. So, okay, so we said, my educational friends say, oh, that's metacognitive skills in action, you know? They realized they didn't know. And then they went into the hints and they played around with the hints until they realized that they did know, and sure enough, their metacognitive skill was correct. That may be the answer, but I can state that it is not the same students who do this all the time. So maybe kids have metacognitive skills sometimes and not others, I don't know. Anyway, so this is another 2 sigma effect, but it says if you're puzzled, you should really go into the hints and think about why you don't know the answer or what you're concerned about, and go into the hints and figure it out that way, rather than using the system to check over whether you're right. Okay, so we don't know. Oh, I said some of this, okay? So that's what I said. We have to do more research. And unfortunately, interesting as that is, it's maybe not on our top of our list right now. Okay, so now I want to ask a question that you probably were all wondered about at some time or other, but were really afraid to ask. And that is, what do the seniors who graduate when they march down the aisle, what do they remember about freshman physics? I mean, do they remember me well, as one of the lines in Bull Durham goes? So we decided to look at that. And then I'll talk about, do we teach them the right stuff? And then our course that does physics. So let's just look at this graduating seniors stuff. So we divide the students into 3 groups. Students who majored in physics or mechanical engineering or aero and astro, which they use mechanics throughout their career. And then student group 1 is people who were humanities or biology maybe, you know, that was pretty unrelated to mechanics. And then groups in the group 2, which is everything else, you know, like chemistry or something like that. And so here's a list of the majors. We did this a priori, okay? We had 55 students, and most of them were in groups 1 and 2. Okay, now I have to explain a little bit about this. The first thing we did was we looked at the mechanics baseline test, and we were blown away. We had taught so well that those students did better as seniors than they did as freshmen. Not statistically significantly better, only like 1/3 of a point or 1/2 a point or something. But they clearly hadn't forgotten anything. Until we looked more carefully, because we actually had data for every question. And what we found was that there was a collection of problems which basically involved mathematics. And that when they graduated from our course, they had a normalized gain of 35%. They'd learned 35% of what they didn't know when they walked in the door. And when they graduated, they had learned 70%. And the correlation's pretty good. Okay, so maybe I should say what's plotted here. This is the score they got at first, and this is the increase in their score plotted vertically. So if they had learned everything, I mean, if they didn't have any points here, they could gain 9. If they already had a perfect score of 9, then they couldn't gain anything. So this curve comes down to 0 there. And if they had gained 7, well, then they could gain 2 if they learned everything they didn't know, okay? So there's 100%, 70%, 35%. Okay, and then we looked at the physics. Then we looked at the, sorry, I have these slides in the wrong, I'm not covering all this, okay. So we looked at the analytical final problems, graded by partial credit rubric. And so what we found was that, that the group 1, which are the red dots on this curve, that they forgot, well, most of what they learned. 60% of what they learned is the best fit for the red points. And again, if they got 20 points at the end of the freshman semester, then the worst they could do was get 20 points lower on the final, namely 0. And similarly, if they had gotten 100 points in the final, well, they could get 100 points lower over here. So that's this forgetting everything. And so the interesting thing is that we call this kind of curve that goes through 0 like that, a pure learning or a pure forgetting curve. And we see pure learning and pure forgetting in these situations, and that they forgot 60, they got only 40% as much credit, which from the previous example means that they were horrible at actually identifying the relevant concepts and applying them. Okay, so here's a summary of the data. This is the group that does English and biology, group 1, and so they lost 50–60%. The chem engineers and EEs and so on, they lost, well, there's a huge error on this, but they lost really pretty much the same amount. And both of these groups, and also the physics majors, they learned the same amount of mathematics after they left our course. Independent, and that's probably in the second semester courses. 802, they learned, in E&M they learned about vectors, and in the vector calculus they learned about vectors, and they learned some more about calculus. And so that surprised me a little bit. Okay, so in addition to that, to seeing how much they forgot, and notice on the analytic problems, the people who still use it still can do it without studying at all. They walked in, but they didn't know what the test was going to be on. The seniors didn't. And there was this physics test, and they did just as well as when they studied really hard the night before as freshmen. And they only lost some of their knowledge on these other, on these conceptual things. Okay, so then we also asked the kids, well, of all the things you learned in this course, which ones actually helped you the rest of the way through MIT? And so here we have the results from that. The yellow is all students. The green are the students who majored in something closely related to mechanics, and the yellow and the red and blue are everything else. So okay, they learned forces and energy. Those were pretty useful. Momentum was okay. Over here about orbits, gyroscopes, rotations, the amount by which the red and the blue groups, the people who did not major in a mechanics intensive subject, that's pretty close to 0. In fact, in some cases it's 0. And it isn't even rated super high by the majors, right? So one has to ask, why do we teach all that stuff? I mean, there's some professional physicists here, and I want to ask you, aside from class, when was the last time you used the parallel axis theorem? Can you just put up your hands? Well, I don't, okay, maybe. I think I made my point, right? You don't need that stuff. It's just like they used to teach Greek and Latin because they thought it exercised the mind. Oh, this is where the students really hit about the formalism, and they have to learn about the cross product and how it, and then they have to learn this differential equation for the rocket equation. Well, they have to be exposed to this at a level where they don't have any understanding underneath it, and that's what we're doing. But that's my opinion. But notice they rated problem solving really high. So that's one of the reasons that that we really pushed on problem solving. But before I tell you about that, I want to just tell you about a survey that we did. So after I've been working on education reform for about 8 years, I said, hey, geez, suppose we're actually teaching the right stuff. I mean, for most of that time, I'd accepted our two-concept final problems as, okay, this is at least a silver standard, by which you can judge the currency, okay? And so I went around and I asked a lot of teachers. Just free response, and then I whittled it down to 12 responses in 4 different categories. And the question is, and you can think about this a little yourself, due to a change in the academic calendar, you have 20% more time to teach the calculus-based introductory physics course to non-physics majors, and the syllabus has not been expanded. What learning will you seek to add or emphasize in this extra time? Okay, so those of you who teach this subject, you might think a little bit about it, and now I'll show you the results. This is par here. So let's just look at the things that aren't close to par. Wider content. We think the whole education establishment, the phrase a mile wide and an inch deep about the math education, probably you've heard that. We teach too much stuff, and we cover a lot and we uncover a little as a result of covering a lot. Okay, so we thought that's our thing we hate. And the thing we love is to teach them to make sense of the answer. Does it make sense that the block accelerates with g when the plane is level? I mean, most kids will just write that answer down and go on to the next question. But if you look at it, it's ridiculous. Does this make sense? Did you have to hit a hammer on this nail 100 times to pound it in? I mean, no one's ever heard a professional carpenter, bam, bam, bomb when it hits the wood, and that's a 4-inch nail, okay? So that you don't connect it up with your everyday experience. You can write down, it takes 100 times. Hit a big nail like that, I have to hit it 100 times. Okay, so sense making is very important. Because I say to the kids, look, someday, someone who works for you is going to come in and say, okay, boss, the cables on the bridge have to be 21 inches in diameter. Gosh, Susan, how did you calculate that? Well, I did it in my computer program. I have my big CAD/CAM program. It allows for thermal expansion, change of viscosity of the air, and blah, blah, blah. Well, do you think it's right at all? I mean, the Verrazano-Narrows Bridge, it's about the same height and about the same load, and they have 28-inch cables. So how can you get by with 21-inch? What if it breaks? It's not too good for our firm or our reputations. So how do you detect whether that's a sensible answer or not? Well, okay, so that's why we think that's important. And notice, we don't think that relation to everyday life is very important at all. I mean, we're not trying to teach them this grunge stuff. We're trying to teach them abstract principles, that F equals MA rules, okay? Well, okay, so I'm just telling you what the teachers think. So then we went out and we got about 600 student votes at different institutions, what they want to learn coming in the first day. And here's the result. It's in purple. Okay, they want wider content. Man, we don't even know this in mechanics stuff. We want to find out about gyroscopes. We want to find out about quantum mechanics and relativity. Why are you teaching this 17th century physics stuff? They could care less about making sense of the answer. They didn't get into University of Michigan by making sense of the answer on those high stakes tests. They wrote down the answer, boom, they went on to the next question, right? What do you do when you have two big homework assignments? You don't puzzle over, do you think that answer's right? Gosh, no, it's not. I got to go back and rework the whole damn problem. I mean, come on. You don't do that. You're trained not to do that. If you do that, you're probably not going to be admitted to a highly selective university, because it's not what they're selecting for. So they don't care about that. They don't care about being able to present a scientific argument. I mean, they're there to learn. They're not there to convince anybody else of anything. Okay, and then they actually would like to know, why is this related to, why should I give a damn about my physics course? Why is it related to my life around me, about how the door closer actually closes the door fast with a little force and then slow with a lot of force? Is that levers? Is that torque? I mean, come on. Okay, so there we are. Okay, so I just want to highlight this. It's not as if we are teaching in directions orthogonal to the desires of the students, the correlation is negative. It's negative 0.4. That's like 120 degrees. They want to go that way, and we're going to that. Come on this way. Come on. And it's a service course. Okay, so I think there's pretty obvious conclusions there. But what's really going on here, I think, is that everybody reads the course catalog and treats it like the Bible. Well, the course catalog says we're going to turn you students into lifelong problem solvers, and so we're going to start now. Welcome to college. We're going to turn you into expert professionals and problem solvers. And the students say, college says, the catalog says the freshman year is for exploration, after which students are able to pick any major. I'm looking for a major. Can you show me why physics is relevant? And that seems to be if you keep these principles in mind and go back to the previous slide, it will explain everything, all the differences. Okay, so I think we should talk to them about why this stuff is important. And finally, okay, I want to talk to you. So after we went through all this and started thinking about, what is it that we want to teach our freshmen? And that may not be the same thing you want to teach your freshmen, maybe especially the ones going into biology, for instance. So we decided it was problem solving. And a typical survey of this is the Colorado Learning Attitudes Towards Science survey. And it has a set of personal questions. This is called problem-solving sophistication. And they're like this one here. After I study a topic in physics and feel that I understand it, I have difficulty solving problems on the same topic. How often have you heard a student say virtually that? Yeah. Often, right? Often, okay? Well, if you agree with that statement, then you're considered a novice, because experts should not, should be able to figure it out, right? After they read it, they should know it. And so that's the Colorado Learning Attitude Assessment. And so but that's the spirit of what we're trying to improve, is the attitude in that kind of question. So our pedagogy, which we call modeling applied to problem solving, and for those of you who know about modeling, it's a distillation of some stuff out of David Hestenes and Malcolm Wells' work, which is very hard to distill. I had to use my humanities skills, which I had to build them up. Because what I didn't realize is that each paper uses the word modeling in a slightly different way, and it's significantly different from end to end. And it's like my humanities friends who know that in this essay that Keats wrote, he wrote this poem right before where he seemed to imply that view, and then in this essay, he had basically that view, but it changed this little thing. I mean, I never knew that. It just all fits in my overall pattern of physics. That's how I learned physics. And that's not what you have to do to learn Hestenes. Anyway, so I claim that it teaches students to solve problems measurably better, in a more concept-based manner, with better organization of their knowledge, with improved learning attitudes, and with positive transfer to a future in the next course, which is E&M. I don't have data on all of that, but I do have data on the performance. And this is the standard deviation from the mean of the kids coming in, and 3 weeks later of the kids going out. Okay, so that's about 1.5 grades. And that's a substantial improvement for just 3 weeks. Now it's intensive, it's 2 hours a day, but they can't do a corresponding amount of homework. So it's mostly the in-class activities. So now about the improved attitudes. Okay. The typical freshman course, according to the paper by Wendy Adams on the CLAS test, reduces the expertise of students across the board in all the different categories that they were able to pull out by factor analysis of their 50 questions. And problem-solving sophistication is this one here. So that gets hit maybe in the 15% range. And our MIT data lie right on top of this curve. I mean, all except 2 of the error bars are overlapping this band here. So that's what our students do. After the 3 weeks course, and averaging the 2 first years we did it together, we got the points in green. And most significantly, this is the one on problem-solving sophistication. On if I lose my formula sheet, I'm dead. There's nothing I can do. I'm not going to be able to solve the problem. Or if I can't solve the problem in 3 minutes, I'm not going to be able to solve that problem. Okay, if you agree with those things, you're a novice, and we reduce the students' agreement with such statements. Okay, and then the next thing is the transfer to E&M. And as far as I know, this is the only such refereed published study, and I don't think I know of unrefereed ones, but maybe someplace on the web there is. And so the key point here is that the mechanics Z-score correlates very well with the E&M Z-score. And you can see that fit for 900 students or something. It's really remarkably good. I think it actually goes through too many of the error bars, but we'll let it go at that. Okay. Notice the slope is 0.7. It's not 1. So it's only, the correlation is only 0.7 if you do, I mean, these are groups of 20 or 30 students, which is why the error bars are small. And it shows there's not other systematic effects that we can easily pull out. But it only explains half the variance. Okay, then we get down to these points at the bottom here. And the year before we offered this review course, a lot of kids got what in elementary school is called a social promotion. That is, that they really shouldn't have passed, but the teacher gave them a passing grade. And so we had an overlap in this region here of skill, about minus 1.2 to minus 1.5, minus 1.1 to minus 1.5, of exactly the same kids who were then compared with their same cohort in the following E&M course. And the kids who were the control group were there, and the kids in our review course were there. And the p-values from either comparing our review course to the straight line or comparing our review course to the control group, the p-values in those things are about 1 in 1,000 or 2 in 1,000. Okay, so that's fairly significant. It's considered very significant by the 5%. But now the next point is, well, here are the kids who were minus 1.5 and below, and we didn't improve their score relative to this expectation significantly in our review course. And the red points are the kids who got F's or D's before, and they were forced to take a whole nother semester of E&M, of mechanics. And although that enabled them to do much better on the mechanics tests, because they passed at that time, they didn't learn any information that carried forward to E&M. And their grade in mechanics the first time they took it is the best predictor of how they did in E&M after taking this other mechanics course again. So what do we do in this course? Basically, we teach students to use a crutch or a standard rubric, a standard approach to problems. Do not write down the equation. Say, what is it, what system are you treating? What are you isolating from the rest of the world and treating as a system? A very important idea in science that I do not know the history of, if some of the education people can say, where did this reductionist idea come from? The idea that it's not the one, that it's just this little thing here, and actually the whole Earth and everything going around here can be accounted for by the viscosity of the air and the gravitational pull of the Earth. And otherwise I can consider this as a completely independent system. That's a very powerful idea. So they have to say the system, they have to say what are the interactions present in this thing, and what one of the basic 5 models, dynamics, linear dynamics, angular dynamics, momentum, energy, angular momentum, which one of those 5 principles, models, are you going to apply here to treat this problem? And so that's an example of these kids doing it, and notice that they also drew the picture there, which is good practice, which we strongly encourage. Okay, so I've been talking for 50 minutes, 51. So I thought I'd just go over the take-home lessons, because I know I put a lot in this talk. The first one is about partial credit grading. Second one, that mastering physics gives 2 sigma gain on analytic problems, but Zotto on more conceptual ones. That homework copying is the largest anti-learning factor, and you must and you can reduce it. I didn't show the slide showing how we reduced it by a factor of 4. A factor of 2, first by going from a lecture recitation format to a studio physics, a scale-up, a large studio physics format. And if you look at the self-reported academic dishonesty surveys, you will see that when the students feel the teacher is going through the motions, blah, 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 and setting the bar that they feel their job is to get over that bar however they can do it. But when you start going around and helping them, and they feel that you're interested in their learning, then they spontaneously do a lot less academic dishonesty, or self-report a lot less academic dishonesty, just of all forms. And we did see that factor of 2. And the second factor of 2 we saw was when we went from the fall, where we grade pass, no record, to the spring, where we grade ABC, no record. We had a lot on our surveys, anonymous survey, we had a lot of kids saying, well, I didn't have to study physics, I knew I was going to pass anyway. Well, actually that's not true, because half of all the kids who passed were in the 16% of the kids who copied more than 30% of their work. Although they started out even, they didn't end up that even. Okay, and then as far as the seniors, I think it's what people have said before, use it or lose it. If you don't practice it, you're going to lose it. Which also raises, when you think about what you should teach your students, why do you want to teach them something like the parallaxis theorem that they won't ever use again and that they will certainly lose by graduation? What is the point in that? And finally, that this MAPS problem solving seems to give problem solving skills that persist to the next course. So that's it.
All right, let's take a few questions.
I have a question which is really just about the last 2 points on that slide, because you teach people problem solving and that persists, but you have to have something via which to teach them problem solving. So why not the 3-axis theorem or whatever it is? I mean, you have to have something. Do you see what I'm saying? I mean,
well, I agree with that, okay, and you're sort of halfway to the Greeks, learning Greek strengthens the mind. But there is, in the case of learning Greek, there's very little evidence that it does. Here, I don't want to comment on that. But I think when the kids come in wanting to know how the world works and how it's relevant to them, instead of teaching about angular momentum, why don't we teach them that they know enough to calculate, look at the weather map and figure out how much energy is there in the high and low pressures, and whether all that energy, if you converted it, would run the country for 3 days, which is the time it takes a new weather system to completely move in. I mean, they might remember that, or whether there's enough rainfall that if you used it all in hydropower, could you power the country? And they can figure that stuff out. And they'd be interested in learning about it. And so why should we teach them angular momentum instead of that? Especially if we know that on MIT, for example, are 100 people who are actually physics majors on the faculty who aren't in the physics department. And they vote on things that impact how our department does. And other people in positions of power may have this bad impression that physics isn't relevant to the world because we just want to teach them abstract principles. And I would like them not to have that opinion. I think the profession would be better off, and the world as well, if they didn't. So I guess that's my answer. Yes, Sen.
I've known a number of people who've applied to MIT and haven't gotten in. I'm amazed that you have that number of students who don't know elementary physics when they walk in the door.
Jens, do you think because they got an 800 on the AP2 test in physics that they know physics?
Well, it's a good. I mean, you know, you're not selecting just on APT. You're selecting on a broader scale.
Yeah, we actually have a 2-axis. You know, one is predicted GPA, and the recommendations go into that, and the other one is sort of character. What did they do? You know, do they build an electric car and race it across the country? I mean, that counts pretty highly. And then we scientists, we wonks, argue with the admissions people about whether we admit the 10 threes or the 3 10s, if you know what I mean. I mean, I think we're asking them to do significantly different tasks than they got into MIT doing. And there's a lot of resistance in trying to do that. We're trying to do it now we're doing fine and doing this in the kids who failed 801 and couldn't take our review, and we taught them in the spring last year. And now in the department, everyone thinks this is great because the course rating is usually 4.5 out of 7, and we got it up to 6.3 by working with the kids. They really felt gratitude. Well, I mean, I think some of the data I presented here is a lot more compelling, but that's not how our place works. You know, and I'm not even sure we're teaching them problem solving. We may just be teaching more confidence. Yes?
That was sort of my question. Do you have any way of telling whether you're teaching them specific intellectual skills or just don't panic when you see a conflict?
Whether you can really what?
Whether you're teaching them, is MAPS teaching them specific intellectual skills narrowly defined, or is it teaching them you don't have to panic when you see a complicated problem?
Judging by the comments, the spontaneous comments that the students made or have made in every year, they say, I liked learning about the process. You know, I liked learning a systematic way to approach problems. And I was sitting in, waiting for the chancellor to finish his important appointment the other day in his office. And a kid barged in from the hall and said, Professor Pritchard, I wanted to thank you for that course 2 years ago. He said, it gave me the confidence, so there you go, to go on in engineering, and which I'd wanted to do. And then he said, and now we're doing thermodynamics, and I suddenly see especially why system is important. So it's maybe some of both. But I think you need both, okay? I mean, they did better. That's the fact, that they did better. Now, maybe there's a more efficient way we could do it. Yeah, there's another question?
How much of this do you tell students beforehand? And does that make any difference?
How much do we what?
How much do you tell of your results here to the students themselves beforehand? Like copying, maybe. That might be the thing you might
there have been a couple of attempts to put some of that data up. And I've put it up. And I've tried to convince my colleagues to put it up. And maybe a majority of them do. But there's a very substantial minority who says, I don't want my students to perceive me as some sort of policeman. I want to have a good, trusting, you know, 60s type relationship with my students. And so I'm not going to do that. So then I know another case where it was done, where the professor gave the web address of the site where you could find the answers, which now is either Course Hero or Cramster, I think are the two big ones. And the result of that scare tactic plus giving the reference was an increase in the amount of copying.
Yeah, it's tricky. We actually show your figure at the beginning of some of our introductory physics courses here. And it's nice for us actually because Michigan students, you know, they have a pretty high opinion of themselves. But the fact that this happens to MIT students is somewhat convincing to them, that it might actually apply to them as well.
Yes?
So a lot of your data was on the review classes. Do you account for students not taking physics again, dropping out, etc.? Or, you know, when you show the improvement on these?
Oh, in the review classes, we typically have a class size of 32, and everybody, I mean, the incentive to take it is and pass it is tremendous. If you pass this course, your grade is retroactively changed to passing. Otherwise, you have to subject yourself to a whole other semester of this stuff. So we have, so everybody stays through the course. And we typically have 2 people that, out of the 30, that I would say dropped out intellectually and didn't really try by the end, and then they show very little improvement. Yes.
One last question.
Do you think any of this research transfers to teaching physics at the high school level?
Okay, the question is, do you think that any of this would transfer to teaching physics at the high school level? And I really have 2 responses to that. The first one is no, not in the present environment in high school, where you have high stakes tests. I mean, I know someone, I just interviewed a postdoc candidate who taught that way in high school. He had learning contracts with all his students, you know, the first week of class. What do you want to learn? What are you going to learn? How are we going to measure that? And the next teacher came in and didn't want to teach that way and pointed out that that teaching the course that way, it didn't qualify as a serious course under the NCAA rules for what athletes have to take certain fracture serious courses, out the door. Okay, so the answer is no. The other answer is yes. There are something like 5% of all high schools teachers who have taken Hestides and Wells and now lots of other people modeling approach to physics. And those people are, if it's done anyway decently, those kids are really learning. And I would much rather have kids who came from that background than kids who know the parallel axis theorem when they come in the door.
All right, I think we're out of time, so let's thank Dave again.